Morning, everyone. So we're going to be continuing through our energy option. So far, we've looked at two different useful energy sources. The first one was fossil fuels, basically burning chemicals that have a store of energy. It ends up releasing the energy that's needed for everyday life. Sort of the downside is when you burn a lot of fossil fuels, because they contain a lot of hydrogens and carbons, the concern is we're depositing a lot of carbon dioxide into the air, and that's causing a natural sort of greenhouse effect that might be attributed to global warming. The second type of fuel source that we've done so far is nuclear energy. So we've looked at both how fission and fusion reaction, they rely on what's referred to as a mass defect. Basically, whenever atoms are being formed, the sum of the mass of the nucleus is actually less than the sum of the individual parts. Where did the extra mass go? Is it actually got converted over to energy. If you just did a calculation for just one particle, the energy value doesn't seem like that much. But you have to imagine here, typically we're dealing with molar quantities of these chemicals. So even if just one particle had a really tiny mass defect, it doesn't take too many particles and this energy stacks up. We saw, although the energy term is convenient for us in units kilojoules per mole, especially for this mass defect stuff here, we found using the unit electron volt or even mega electron volt was actually better for our curves here. We actually saw that both fission and fusion increase the binding energy per nucleon, and therefore both the breaking up fission and the joining together for fusion ends up releasing energy. Today we're going to step into a new section here on solar energy. Turns out the energy that we get from our sun is actually the ultimate energy provider. If you think about our fossil fuels, it was plants millions of years ago that had photosynthesized, that had stored some of the sunlight's energy. Sure, over time, over pressure, over heat, it got sort of condensed and compacted into what we now use as crude oil, petroleum, different fossil fuels. That's still harnessing the energy from way back when. We call that a non-renewable source because we can't regenerate our coal as quickly as some of our other sources here. So there's a constant push towards trying to switch to alternative energies, try to switch to more renewable sources that are not only more environmentally friendly, that can be replaced on our time scale. So we're going to have a look at solar energy. On this slide here, you see like a system of solar panels here. Solar panels can also be called photovoltaics. They take the light energy from the sun, and they generate voltaic, they generate some voltage. We're going to come back and finish up with C8 a little bit later on in the section here. That part's going to look at semiconductors and how these solar panel arrays are actually constructed. But what we'll do right now is just the C4 section just to start introducing to you what we know about solar energy so far. So let's have a look through our slides here. We're going to begin just a comparison here between a nuclear power plant versus our solar panel sort of design. A nuclear power plant here, like we mentioned, all of our power plants so far have been modeled after fission. We haven't been able to harness fusion because that takes maintaining plasma, really hot ionized gas. It's really hard to confine, still not yet successful. So for nuclear power plants so far, we take, there's two primary designs. One is using uranium. Uranium has two possible isotopes. Uranium-235 is the fissionable one, whereas uranium-238, which is more common, is not directly fissionable. So what we did is, if I was building a uranium reactor, I would actually need to enrich the uranium. I would need to select for the lighter isotope, and I would utilize the uranium isotope for the fission reaction later on, except we saw that whether you are selecting for it through gas diffusion or through centrifugation, you have to run it through a long cascade of centrifuges. You have to run it through, repeat the process of separation many times before you can gradually enrich it even ever so slightly. We found that more modern of a design here is actually using plutonium. You can take the uranium-238, which was non-fissionable. You can actually, through neutron capture, you can get it to form a plutonium molecule. Plutonium is chemically different from uranium, so separating uranium from plutonium is fairly easy. And plutonium is said to be a breeder reactor or breeder reaction style. Basically, we take what would have been waste out of our uranium reactors. We get a whole pile of this plutonium, and we manage to do fission on plutonium and itself also produce a lot of energy. Both of these style of power plants here, they basically convert the mass defect, that energy here, first into heat. So usually it's used to heat, let's say, a body of water. Definitely we'll need to have cooling in different areas so that we don't overheat. But basically we have this energy transformation between nuclear energy first to heat energy. We somehow convert that heat energy into sort of the kinetic energy, speeding up gas molecules, trying to coordinate some randomized gas motion to more coordinated fashion. And then eventually, due to maybe a coordinated motion, it ends up running a turbine for us. It gets converted over to electrical. Although in the first law of thermodynamics, we say energy is always conserved, the total quantity, the number is unchanged. We saw that because of the second law, we're always fighting this losing battle. Every time there's a transformation, we end up losing some heat. Heat dissipates due to heat, and that's no longer available for us. It's no longer free energy. Let's contrast this slide here with our solar panel or with our solar energy design here. What we're going to see is maybe your angle is still the electrical energy, but solar panels, in contrast, are a lot more simple. Solar panels directly take the energy. You could be ultimately from the sun, or this could be just everyday old light bulbs, things like that. But we can convert light energy over, and we're just doing one transformation. We still are going to lose a little bit of energy because we are converting the energy form. But you see that there's less energy transformations, and therefore that would imagine we would have a better efficiency. We'd be able to maintain more of our electrical energy. So. Again, we're going to take a look later on at how solar panels are actually designed, at these photovoltaics. How do they actually capture the sun's light energy? Today we'll start off with the biological analog. We basically look at how do plants do this naturally? How do plants millions of years ago store those in high energy sugar molecules, even long since they've died off and decomposed? How come we can still harness the energy that's stored within these chemical structures and actually utilize them for our combustion fossil fuels? So let's have a look at our sort of plant analogy first. How do plants actually convert light energy over to electric? You probably heard of this word here. Plants or other producers, they can do what's called photosynthesis. They can take the light energy, again, primarily from the sun, and they can actually synthesize high energy chemicals. So this is a sample of a photosynthesis reaction here. They're taking primary ingredients like carbon dioxide, like water. Those are really common ingredients in the atmosphere. They absorb the light's energy. So this is a net input of energy is endothermic, and they end up storing that light energy here into different sugars. They're starting off with the simplest of sugars here, the C6H12O6. This guy here is glucose. It's sort of a monomer of a sugar. Sugars come in a whole different family. Sometimes sugars can end up forming dimers and longer chains, but at least for the just for our understanding, we're just starting with a very simple sugar. So plants do this naturally. They photosynthesize. They, in some sense, they take in carbon dioxide and they breathe that, and they end up producing this glucose molecule. Us as consumers, we end up eating these veggies and different plants here, and we basically, in harnessing the glucose, we then undergo combustion of these glucose. In some sense, it is a burning reaction, although you can imagine the burning inside our bodies have to happen a lot more naturally. We call that process cellular respiration. It's basically taking the energy stored up in all these high energy sugar molecules, and actually, sure, the byproduct ends up being CO2 and water, which we're concerned about, but at least it's a good energy source, energy provider for organisms. So how do plants harness this energy from sunlight to produce the glucose? So we're going to look primarily at sort of the insides of a plant cell here. For a plant cell, you can imagine like a hard cell wall, different organelles, different structures here. There's one particular organelle that is specific to a plant cell. Underneath the microscope, it actually does look green to us, and those organelles there are actually called chloroplasts. So here's a zoomed in picture here of a chloroplast. We're going to see chloroplasts are really easy to recognize. When you take a cross-section, they have all these little stacked discs, stacked plates. I believe these ones here are called stomas. And basically inside those stomas, inside these little stacked plates, is a particular chemical model called chlorophyll. The chlorophyll here actually looks green to us. If you remember back into our chapter 3, transition metal, color, things like that, the reason why something looks green is not because it's absorbing green. The reason why it looks green is because it's absorbing the opposite of green. The other color light, the complementary color, can't get through, and therefore green is what is overall transmitted. And overall, it's this chlorophyll molecule. We're going to take a look at its chemical structure and try to discover what is it about this molecule that allows it to absorb the complementary color. Complementary to green would be something like a reddish, yellowy kind of light. What is it that allows it to actually absorb that color and thereby transmit off the green color that we see? So We're going to have here light can be absorbed by the chlorophyll. So this is a large molecular structure and as well as other pigment structures because they have what's referred to as a conjugated electronic structure. So that's a super important note there, that wording here, conjugated electronic structure. What is it? Let's look at a few examples. So starting with ethene, that's sort of our base model here. And as we step over to these other molecules shown on the diagram here, we slowly get some conjugation. So let's see if you can spot what is it about these molecules here that they have in common that might be referred to as this conjugated electronic structure. Hopefully you were able to point out to me here, well, you notice that there's some double bonds. They alternate with double, single, double, single, double. That's exactly the structure that we want in terms of this conjugated structure. So if they ask you what's the specific feature that allows plant cells or chlorophyll molecules to actually absorb light, it's this conjugated system, and you'll recognize a conjugated system just with these single and double bonds alternating back and forth. So here's a sample picture of a chlorophyll molecule. You notice it's like a larger biological molecule, but you notice there is that conjugation, that alternating single and double bonds. Sure, there's a lot of fused rings and it makes it more complicated, but it is that notion of having more conjugation, having the double, single, double alternating. In fact, you see on the next slide, the more conjugated it is, it actually affects what wavelength is actually absorbed. Especially as the conjugation gets longer, it can start absorbing in the visible color. Whatever is absorbed can't get through. We end up seeing the color light that ends up getting transmitted off. Why this conjugated system? Why does it matter that there's this double, single, double sort of nature here? We know the electrons that make up that double bond are actually pi electrons. So those pi electrons that are present in the double bonds, they can absorb light energy. And now this light here can range in many different frequencies here. When they absorb light, they can be excited to a pi star energy level. So it's basically jumping an energy gap here from sort of the bonding orbitals to the anti-bonding orbitals here. And what we're going to see here is as the conjugation increases, as the length of this double, single, double pattern gets longer and longer, we're going to find that the energy overall required for your excitation actually ends up decreasing. So we have a nice table here. Starting off with ethene. Ethene here only had one double bond. You'll notice it's lambda max. Again, it's not a like only absorb 175. It doesn't absorb 174, 176. But it's telling you this wavelength here is the peak where the absorbance is highest. Now you see that those ones there are heavily in the UV region. Those would just basically absorb straight through and we can't actually see any color to that. But as I go from ethene to butadiene to hexatriene here, the length of the conjugated system actually gets longer. Butadiene had the double, single, double. Hexatriene here had more. The longer the system, you'll notice that this wavelength here actually gets higher. Wavelength and energy are opposites, so if it's a longer wavelength, as the in the orange text there it says, the energy required is actually less. In fact, by the time you get to beta carotene or even chlorophyll, that large structure that we saw before, when we get this conjugated system longer, you notice that this energy requirement actually decreases even more. We start absorbing in the visible region, and again, the color that we end up seeing is what's left over from what couldn't get through. So for example, beta carotene, that's used in a lot of our carrots, are very primary veggie that has this here. And basically here we know carrots look orange, but that's because it's absorbing the 450, the bluey violet end of the spectrum, whereas by the time we get to chlorophyll, it looks to us blue-green as a pigment, but that's because it's absorbing the 750s, the more reddish wavelengths. So make sure you can identify it is this sort of conjugation aspect that ends up making it absorb different colors of light. We're going to switch gears here now, and so that was the sort of plant analog here. We're going to see how we can actually mimic our photovoltaics, our different semiconductor systems here to look like a chlorophyll later on. But let's just take another lens here and take a look at what else we can do to glucose. And we're going to end off here. Well, for glucose, we can actually run it through a reaction called the fermentation procedure. Through fermentation, the glucose is actually converted into another fuel called ethanol. Ethanol is something called a biofuel because we are taking what would have been a sugar from a living organism and we're using that directly as fuel. Other synonyms for this here would be diesel fuel or vegetable fuels, things like that. So we're seeing while you can definitely burn glucose, it's a high energy store of energy. If you end up doing fermentation and you interconvert it into ethanol, this is not the only fermentation reaction it is, but we can convert it into other fuel sources as a family called biofuels, and we can actually burn these biofuels directly. So they're introducing to you here, I would memorize this equation to actually form ethanol. This ethanol here sometimes is used as a gasoline additive. Hopefully it's used to up the octane number. If you look back at that section, ethanol actually had an octane number of, I think, 107 it was. It's even better than our standard reference, our isooctane 2,2,4-trimethylpentane. Or you can just burn ethanol directly. So ethanol by itself can actually be used as a biofuel. What's nice about this section here is sometimes other agricultural industrial processes end up generating a lot of ethanol. It would have been just waste alcohol or waste fuel here, and here we are trying to harness or recycle some of that waste into more usable energy again. So that there is ethanol. It does have some advantages and disadvantages, just like with all things here. Let's start off with some advantages. The advantages here of burning biofuels like ethanol. Sure, whenever you do any burning reaction, it ends up releasing carbon dioxide and water. This is at first not going to limit the amount of CO2 that we're putting into our atmosphere, but it's said that ethanol here, because the carbon source that it would have started with was actually carbon dioxide that the plants had absorbed way back when, we refer to ethanol here, this burning reaction, as being carbon neutral. If I had 10 molecules that the plant cell actually ran through photosynthesis, after I burn it, I'm just going to end up with 10 carbon dioxide molecules later on. Overall, I'm not adding any net amount of carbon dioxide. So that's why that's referred to as a carbon neutral source. So overall, perhaps lower greenhouse emissions. We're not taking otherwise coal or crude oil that was in the ground here, not carbon dioxide, and then burning those here too quickly to be replaced and actually throwing in a lot more CO2 in our atmosphere. It helps us have a reduced dependence on oil. So most new cars can actually run on a blend of gasoline and ethanol, although they do need to actually design engines in different fashions. So, what are some disadvantages, however, here? Back in the first lesson, we talked about when we're considering the energy source, a useful energy source here has to be able to provide a lot of energy at a reasonable rate. One way of tracking how much energy it provides is called specific energy density. Like I mentioned before, specific energy, if I see specific, I think of the term mass. So if I'm carrying this fuel, like a canister of propane, the specific energy will tell me how heavy would that propane canister be versus how much energy I'm getting off. If you have the actual physical density of it, you can convert it over to something called energy density, especially for liquid fuels here. It might be nice to say, well, how many canisters, how many volumes of liquid am I actually burning to provide the energy that I need? So those two are sometimes more useful than just looking at a combustion enthalpy. Combustion enthalpy is on table 13. Unfortunately, only give you sort of per mole. But in this case here, we're just broad stroke, we're more just general, and we're saying, well, if I burn this fuel, how much energy can I expect to get? So if you do the math here, you actually realize it takes more ethanol, like more volume of it, to actually provide the same amount of energy as 1 liter of gasoline. So therefore, we can say the energy density is actually lower. So it doesn't provide as much energy per volume of the otherwise fossil fuel. It could potentially damage the engine. So ethanol here, because it has a hydroxyl group here, it's actually available for hydrogen bonding. So it can actually absorb moisture from the air, which can lead to engine corrosion, let alone some engines aren't actually designed for actually burning ethanol directly. So you have to watch out for that. Don't put diesel fuel into your gasoline engines and vice versa. Let's end off with this slide here. Sometimes there is a very high energy cost of production. So ideally, we would just I run an agricultural process and we end up with a huge supply of ethanol just sitting around left over. If I can recycle it, great. I would have had the ethanol anyways. But if you are now going into it saying, well, ethanol can be a substitute, if I'm having to actually artificially and actually directly create ethanol, by some calculations, it's a really high energy cost, a high carbon footprint to actually produce the ethanol, produce the biofuel here, and burn the biofuel in your car. So by some calculations, it's similar, so it may not be as advantageous as what we would expect. And lastly here, I like this phrase here, is a food versus fuel sort of debate, especially when we're starting to use some of these biological crops here. We're harvesting them, in this case here, not for food reserves. It's not for actually consumption, for eating. We're actually just sort of, we're growing a bunch of ethanol feedstocks, things like that, and we're actually diverting them over to burn as fuels. There's going to be a sort of food versus fuel debate where if you start doing that more, it's going to drive up the price. It sort of lowers the supply of different agricultural products like corn. It's going to drive up the price. Some poorer countries here might end up doing the exporting, focusing more on the economics of actually using biofuels, but leading many populations to be vulnerable for starvation. So this constant dilemma between food versus fuel. Fuel is nice because it provides our energy source that we need to do our everyday life, but at the same time, we also need food for our survival as well. So with any new invention or new design, there's always some pros and cons for it. So let's flip over to our textbook slides and let's have a look here. Okay, so continue on here with our solar energy section. Let's scroll down here. So this is C4 here. Solar energy here is said to be the ultimate energy source. So even if you think about our fossil fuels, like we mentioned, those are plants that had harnessed solar energy from millions of years ago. It got processed under high pressures and high temperatures into the crude oil reserves that we use. But ultimately here, that energy here would have actually come from the sun as well. We have fusion reactions in the sun. Again, we haven't been able to harness it in an economical and practical fashion on the Earth. But the sun, while it's really hot here, how does it actually generate all this energy here for our use? Is it actually undergoes some of that fusion reaction that we just talked about in the previous lesson. So 98% of the sun's energy is emitted as heat and light. Luckily for us, this electromagnetic wave here can travel through the nothingness or the vacuum of space. The remaining here, there's some lights that are invisible to us here. They actually does emit some X-rays and gamma rays as well. They always, in this option here, like asking you to qualify some advantages and disadvantages. So in this case here, looking at solar energy, some things just introduced to you here. The solar energy here is typically available where you need it. So you don't need to transport or store this light energy here. As long as it's a nice sunny day, we can end up actually utilizing the energy directly. Now, of course, sometimes the solar energy here is wildly dispersed here. So unfortunately, you might need to concentrate it. So that becomes more of a disadvantage here. The same idea here. So in Vancouver, we don't get too much sun, especially in the winter times here. So our supply, can you actually run on less energy if it's a less sunny day, right? So that can be a sort of more consideration for you. But otherwise here, it's a very clean, safe energy source here. It's directly converting light energy. We're not dealing with any burning. Plants naturally do this anyways, and it typically is smaller environmental impact, smaller carbon footprint. So some ways the solar energy here can be collected. So we can directly design things like solar panels here to actually actively convert the sun's rays. So using the sun to cause endothermic changes. So you can have, again, as mentioned here, photovoltaics. You can directly convert the sun's energy directly into molecules that you want, or a more sort of passive one here. You just leave out a body of water and you let the sun naturally heat it up. Now the water is hotter, and as that water cools, you may be able to harness, convert that thermal energy passively into other forms. Usually the goal here is to convert everything into electricity, because electricity then can be delivered very far distances. Electricity can then be interconverted. If you have a light bulb, I can reconvert it back into light. If it's a heater, I can reconvert it into heat energy. Electricity is a fairly versatile form of energy. So we talked about capturing it indirectly using, so photovoltaic here is basically a huge array of photovoltaics are called the solar panel. We'll come back and take a look at this dye-sensitized solar cells later on in this unit here. And we basically use the plant analogy. How do plants actually harness this energy? The key word here is photosynthesis. I'm going to show you some of these reactions a little bit more in the upcoming lessons, but for the time being, you should note that photosynthesis takes raw ingredients like carbon dioxide, like water. It absorbs abundant light energy. As a producer, ends up producing high energy sugar molecules. We're just going to use glucose for argument's sake here, and basically it's stored some of that light energy. Maybe animals eat these plants, and we end up eating these animals here. Yes, every time there's a transfer, even the first animals, the first consumers that eat it, they're going to have already some loss due to energy as we then eat the animals. There's also going to be a little bit of loss of energy as well. So that's why we sometimes need to consume enough food so that we can have enough energy to run our metabolism, run our everyday functions. But there we go. That's photosynthesis here. Plants don't cover the entire surface of the earth, so it's inefficient, but it is crucial. So there is a sort of push for, let's grow more trees and grow more plants so that they can harness the energy that otherwise would be there anyways. We don't need any fancy designs, not expensive photovoltaic sort of equipment, and basically it can absorb all the solar energy. Make sure you know how do plants do this. Plant cells have an organelle called the chloroplast, and inside the chloroplast is our key molecule here called the chlorophyll. Chlorophyll, carotenoid is another pigment molecule here. And basically here, remember, the chlorophyll itself, it appears green, but that's because it absorbs the opposite color. For a carotenoid here, like for a carrot, like beta carotene, things like that, it appears orange for us. So it looks like this, even visually, even without any microscopes, but it's because it's absorbing the opposite color. They have an interesting note here. Let's say in the springtime and the summertime here, actually plant cells will naturally have a proportion of some chlorophyll and some carotenoids here. But because there's so many more chlorophyll molecules, we end up seeing the leaves as green. In the fall time or in the autumn times here, the chlorophyll molecule actually degrades quicker than the carotenoid molecules. So that's when the leaf color actually changes color. We're actually seeing those carotenoids that were actually present previous, but we end up seeing more of the autumny orange color. So for this section here, keep in mind that color wheel here. So Roy G. Biv here. We say a chlorophyll here looks green. Again, that's because it's absorbing more of the reddy, orangey wavelengths. So we always see or we observe the complement. And I prefer you to say words like the complementary color here is transmitted as opposed to emitted, because it's not electrons falling and giving off this color. It's actually just what's remaining over, what's left over from what hasn't been absorbed. If you flip over the page here, this is a key term. Make sure you know this one here. How do plants do this? Or what are other molecules? How does chlorophyll actually absorb light energy? You have to be able to know here it's because of this conjugation. Conjugation here is a system of alternating a double, single, double, single, double. It doesn't have to be through the entire molecule. We saw that for the chlorophyll molecule, but at least you have this conjugation system. You can actually be absorbing different colors of light. At first, when I had ethene and just butadiene, if the conjugation was short, it was absorbing the UV. Well, we saw that the more extensive or the longer the conjugation, you end up absorbing a higher wavelength. Remember, if I absorb a higher wavelength, I actually need less energy for that excitation because I have a longer, more extensive system. Those pi electrons can more easily, so you can make a note here, pi can absorb that energy, can become pi star easier with longer conjugation. Right. So benzene molecule here, which has this sort of 3 double, single, double, that pattern here, it can absorb longer wavelength than just something that was 1 double bond here, and the longer the conjugation, the higher the energy absorbed. So I showed you a table on the slides here. Here's another sample table. You'll notice a lot of them, if you only have the odd double bond here or there, a lot of them are absorbing the UV. These will still look invisible to us. But as we start getting to those hexatriene and chlorophyll, beta carotene, which has 11 conjugation, much longer conjugations, we end up absorbing in the visible region, and then it ends up showing off the color. They actually utilize this in some sunscreens here. They have this guy here called PABA, so you actually see this on some of your ingredients for sunscreen here. This one here, if you look at the structure, also has some conjugation. It's not in the visible region, so it's going to still look colorless to us, but it is able to absorb some of the damaging UV radiation from the sun and actually protect us from the sun's rays. So here's just a little bit more detail for the chlorophyll molecule. Chlorophyll contains a porphyrin ring. A porphyrin ring here, it's a long description here, 4 planar heterocyclic chiral rings, like a picture here. This guy here is a porphyrin ring. And in fact, when you actually look at this porphyrin ring, you actually end up seeing that the porphyrin ring actually has this nice double, single, double, single, double, single, double, right? It has this conjugation system basically all around this ring. Sure, chlorophyll is a much longer molecule, it's a larger molecule than that. In fact, there's 2 close forms of chlorophyll that naturally occur. Chlorophyll A or chlorophyll B, they only differ in one small R group. The porphyrin ring is still there in both of them. There's a long chain. Notice this says C20, so this chain here that actually extends for longer. But for this R group here, if it happens to just be a methyl group, that's one form of chlorophyll, chlorophyll A. If it's an aldehyde group, a CHO group, like a C110 single bond H in its terminal, that one there is chlorophyll B. It still has this porphyrin ring, although the color it's exactly absorbing. It might be different. So we actually have an advantage here. If I have these two forms, I have the extensive conjugation, I can absorb visible light, but as I switch off these R groups here, the color of light, the lambda max actually changes a little bit. So together we can actually capture more of the sun's radiation. So it's a more extensive conjugation. It can absorb visible light here. Together they span a larger region of EM, so they can absorb more solar energy than individually. In contrast here, we have the other common pigment here, which is called the carotenoid. So this is actually the most common pigment they say in nature. It looks to us yellow, orangey, kind of greeny color, reddy color, and that's because it's absorbing the violets or the greens. Carotenes are a subclass of carotenoids here. Carotenes are only hydrocarbon chains. So these are only things that have CX, HY. They only have C's and H's. They don't have other oxygens and other elements in there. So here's alpha carotene, beta carotene. You'll notice again very similar in terms of structure. I'll leave it for you to see if you can actually figure out what's the difference between these two here. But mainly what we're looking for here is this double, single, double, single, double. It's a fairly extensive system. The longer this conjugation system here, the higher the wavelength, so lower energy needed for this absorption. When you look at that photosynthesis reaction from the last page here, photosynthesis can actually be divided into two half reactions. Now, we had done this a lot in our redox chapter and trying to balance it here. We see that overall, yes, we are taking carbon dioxide and water over to form glucose here. You can actually figure out which part gets oxidized and which part gets reduced just simply by looking at oxidation number. So for example, this carbon here starts off at a +4 state. Careful for oxidation number has to be sign first in the number. And then in the other case here, oxygen would be a -2. There's 6 of them, -12 plus that. So in this case here, carbon is 0. If I go from 4 to 0, my oxidation number dropped. We know that's a reduction reaction. In a similar way here, when the oxygen goes from, it's -2 on the left-hand side here, but when it goes to elemental state here, I have 2 oxygens actually gaining by 2. In that case there, that one there is oxidation, and evidently it's going to be oxygen in the air. Oh, sorry, I actually mentioned, I meant to say it's actually the water that actually undergoes that. So using some of that redox chemistry, we can actually predict, oh, this is actually a redox reaction here. It is overall endothermic, so we would expect the delta H here actually being positive, and that's actually a store of solar energy. And just towards the end here, we'll flesh out a little bit more with vegetable oils and how we can actually utilize ethanol directly. But let's just look at some general pros and cons. As I mentioned, I would memorize this equation here. This equation is called fermentation. So it's basically converting those sugars that are produced from glucose over into ethanol reserves. Ethanol can also be found in sort of waste products and a lot of industrial processes here. And basically what can happen here is we can end up designing engines that actually run off blends of not just pure gasoline, crude oil. We can actually sort of supplement it with an additive. This additive here actually has a high octane number. So we can actually have, in this case here, they're introducing here gasohol. It's a 1090 mix of this gasoline here. Very useful because it is a liquid. Liquids will run through our engines very easily, easy to store, easy to transport. And then some advantages here, as you start relying more on these ethanol fuels or biofuels, diesel fuels here, we tend to decrease our oil dependence. We don't just straight rely on crude oil. The disadvantage I mentioned, because there is hydrogen bonding for that hydroxyl part here, it ends up forming hydrogen bonds, so it ends up absorbing atmospheric water here. This can lead to rust or lead to corrosion problems. So it can sort of have more wear and tear on our cars. There's lower emission. We had talked about, we'll see it more on the next slide as well. The ethanol burning is seen to be carbon neutral because those carbon dioxide would have already started off in the atmosphere, but we saw that as a disadvantage in the time and the energy and the different reactions that it takes for you to create this ethanol here. It may have had the same carbon footprint as gasoline, if not more. So they end off here just making comparison here. Methanol can also be another sort of biofuel. They're just talking about here what other, so methanol here has a lower specific energy than a fossil fuel, just like ethanol had. We talked about a synthesis gas mixture in an earlier lesson here. We had formed methanol, which is our primary component of natural gas. So we can use this directly. Unfortunately, when you burn this one here, this typically leaves behind a lot of soot residue. There's a lot of unburned, so it's a very smoky flame here. It could be byproducts and really toxic gases of CO. So you have to just be careful when you're designing engines. For example, our engines have what's called a catalytic converter. It can convert some of these more deadly gases into a more stable state and a more state that's easier to work with, so we don't accidentally poison ourselves here. Sorry, I meant to say methane is actually the highest component of natural gas here, and they say, well, you can actually take our glucose or sugars, you can convert them over to form methane. This is how you can make methane, and then you can burn that methane here as actually our source of energy. So I'll leave this lesson off there. Tomorrow we'll come back, look more detail at vegetable oils here, and specifically at viscosity and particular organic reaction they do. Thanks, guys. Take care.